some of our traits are sex-linked. So sex-linked traits, which means that I have an allele only carried on a sex chromosome, so either on the X or the Y, but almost always it's going to be carried on the X. And that makes sense because, as we've discussed, the X chromosome is much larger than the Y chromosome, so there's more information on that, more alleles. So some examples of some sex-linked traits are red-green color blindness, so not being able to differentiate between the colors red and green. Hemophilia, which is a blood clotting disorder, which means that if you get a cut, you just keep bleeding and your body doesn't clot to form the scab like it's supposed to. And then another one is male pattern baldness. So, when guys lose their hair at sometimes a younger age, that is also a sex-linked trait. Okay, so how is this going to look in our genotypes and our phenotypes? Well, we have a chart here to show us. So our genotypes are always the alleles, or the letters. So the first two that I have here, those would both be males, which makes sense because it's an X and a Y in both cases. The difference between the two is that the first one has a capital N on the X, and the second one has a lowercase n on the X. So when I see a capital N, that means normal or not with the disease, whatever it happens to be. So X capital N, Y, it would just be a normal male or a male that does not have that disease. And X lowercase n, Y means that the male does have the disease. Again, notice that the only times I use the capital N or the lowercase n is when I have the letter X, because as we said over here, it's almost always on the X chromosome. Okay, so that's the guys, pretty simple. Either they have the disease or they don't. The girls are different because they could get one capital N X from mom, and you could get one from dad, which means that they're a normal female. They don't have the disease, whatever it is. This one is different because now I have X capital N, X lowercase n. So a normal one from mom, a recessive from dad, perhaps. And now I have, it's still a normal female because I don't have two lowercase n's. If so, then it would show the recessive trait like we've been discussing. So this female is going to not have the disease, so she'll be normal, but she's going to be what we call a carrier. She can pass that along. And then in the last case, the only way I could get a diseased female is if they had the recessive X from mom and the recessive X for dad. So we show that here with capital X lowercase n, capital X lowercase n. So I can use these genotypes for any of these sex-linked traits to find out who is normal, who has the disease, how many are guys, how many are girls, etc., etc. So it says here to notice what is required for the males or the females to have the disease. So in both of these cases, I have, in a male, I only have to have one lowercase n on the X because they don't have another X, they have a Y. So just one recessive allele will cause the male to have the disease, where with the female they have to have two. So hopefully it makes sense that in any of these cases, any sex-linked traits are going to be more prevalent in a male than a female because they only need one recessive. The female needs two. So let's practice across. So I have a normal male with a colorblind female. So colorblindness, we said, was one of those sex-linked traits. So she's definitely going to have the two recessive. The male is normal, so he has to be XY. Then we have to decide, is the N capital or lowercase? Well, it's capital because he is normal. He does not have the disease. Another way you could write this, or you might see it written, is like this, with X capital C Y, meaning that he's not colorblind. The C is for colorblindness. And over here, my female is X lowercase c, X lowercase c, so lowercase is recessive. Now, why do I kind of prefer this one up here at the ends? Well, it's a lot easier to tell the difference between a capital N and a lowercase n than it is to tell the difference between a capital C and a lowercase c. I tried to make it really apparent here, but when you're doing these on your papers, it's a little easier to see the capital N and the lowercase n. So either way is accepted, but this way might be easier. Okay, so I set up my Punnett square, just like I always do. So I have the male alleles on the top, female alleles on the side, and then I fill them in as we've done many times. So I'm just filling them in, and then I'm going to look at my genotype and phenotype ratios. Again, nothing new. So I noticed that these first two boxes are XN, so X capital N, X lowercase n. So I have 2 of the 4 boxes doing that, so that's 50%. The other 2 I have X lowercase n with a Y, so I have a diseased male, but for now we're just genotype, so it's just the letters. So it's X lowercase n Y, and I have 50% of those that way with those letters. Okay, so phenotype is where it's going to get a little trickier. So when I see that 50% have X capital N, X lowercase n, what does that mean? Well, it means she's a carrier female, but she is normal. So I have 50%. We could say it as carrier female. We could say normal female, and then maybe in parentheses write carrier so that we can distinguish between the two. And then the other ones that I have 50% diseased male, or in this case, since the disease is color blindness, we could say 50% colorblind male. We have one extra question on these ones. What is the probability that their children will have the disease? Okay, well, if I look at my phenotypes, I see 50% of their children could be female and they would be carriers. The other 50%, if they have a boy, they're going to be colorblind. That boy will be colorblind. So I have a 50% chance that the children will be colorblind, and in this case, the only colorblind children they could have would be males. So with our last video, we had 3 problems, same idea this time. So take a few moments to write this down, pause the video, and then try it on your own. Problem 2. And problem 3.